The internet operates at an incomprehensible speed, with fiber optic networks moving vast amounts of data across oceans in milliseconds. Yet configuring a web domain and adding a single line of text for ownership verification requires a wait of up to 48 hours. This specific delay is commonly referred to in the industry as DNS propagation. Engineers often assume this wait is a result of physical latency, a system error, or data slowly traveling across the globe. This delay is a rigid, mechanical necessity dictated by the core architecture of the internet. Understanding the 48-hour window requires looking directly at the underlying network architecture rather than relying on metaphors. The technical explanation for the delay is this. We added a TXT record to the authoritative DNS server, but the verification side's full resolver retains an old cache. We must wait for the TTL to elapse. That single statement contains the core mechanics of a global DNS query. By deconstructing this sentence and isolating each highlighted term, we can identify exactly where the temporal bottleneck occurs. Mastering these specific components shifts our perspective from a passive user waiting on a loading screen to an architect understanding a distributed database system. We begin with the first term, the TXT record. This is the payload we are attempting to move. Standard DNS records typically handle routing. An A record points a domain to an IP address, while an MX record directs mail traffic to a specific server. The TXT record does not route traffic. Instead, its value is an arbitrary string of cryptographic characters. In a verification scenario, this string serves as a cryptographic key. The host server receives this static string and holds it, waiting for an external system to read the data. Because the TXT record is a static, non-broadcasting payload, the 48-hour delay must occur during external discovery rather than within the record itself. The payload is held within the authoritative DNS server. Global domain records are not managed by a single central master ledger updating all nodes simultaneously. The DNS is a decentralized, hierarchical tree, starting at the absolute top with the root. Resmart finality delegates downward from the root to top-level domains, such as .jp or .com. This branch ends at the authoritative DNS server, which holds the definitive record for an individual domain. The newly added TXT record exists only within this specific bottom-tier node. To verify the domain, an external service must physically traverse this entire graph from top to bottom to retrieve the string. Because data exists at the extreme edges of a decentralized hierarchy, real-time global synchronization is structurally impossible. We now look at the verifier's perspective through the full resolver and the TTL. If every global query traversed the tree to the authoritative server simultaneously, host servers would collapse under the load. The full resolver acts as the verifier's intermediary, using aggressive memory caching to prevent such a collapse. When the full resolver checks its local cache, it finds the old state of the domain, which does not contain the new TXT record. The full resolver is prohibited from bypassing this old memory to query the source because of the time-to-live protocol. Every piece of cached memory is attached to a TTL, a strict mathematical countdown timer. A TTL of 3600 dictates that the resolver must wait exactly 1 hour before it is permitted to request fresh data from the authoritative server. This creates a mechanical lock on the query path. The external world remains blind to the new TXT record until this localized timer hits 0. This DNS waiting room is actually an intentional, strictly localized memory freeze, governed entirely by the TTL integer. During the 48-hour wait, the new data sits isolated while an enforced memory freeze persists. When the TTL timer reaches 0, the old memory dissolves, lifting the barrier. The full resolver immediately queries the server, successfully retrieving the TXT string. The verification logic executes successfully the moment the local cache expires, confirming the configuration was correct from the start. We return to our initial technical explanation. We added a TXT record to the authoritative DNS server, but the verification side's full resolver retained an old cache. We had to wait for the TTL to elapse. This technical statement maps the mechanics of a distributed database interaction. Because the data does not move or broadcast, the term DNS propagation is mechanically inaccurate. In reality, external nodes simply wait passively for their localized timers to run out. The 48-hour delay is an intentional architectural trade-off that maintains global network stability at the expense of instantaneous synchronization.